So we look at high-resolution timing of those packets. And what I try to make a point here, follow up on what John said, is I would like to show you that it is a threat. It is an obvious threat and has implications on confidentiality of traffic and on security as well. What I also want to show is that countermeasures are very hard to come by. And I will show this in the case of link padding. Oh, sorry, let me go back. Also, one has to be extremely careful. If you don't do things right, you're actually counterproductive. You do things the wrong way. You make it easier rather than harder. Also, what I will show at some examples is that you cannot hide in a crowd. So we always have the hope that as long as we are many, we can hide. Well, we cannot. I will show you that we can get you wherever you hide. And I'm going to show that with wireless world coming down, it's even going to be worse. And I'm going to wrap up on some work on voice over IP. This is work. This is just one picture on work that Dave Wagner and his students did a few years ago and presented at Usenex. This is an application of capturing packet data on an SSH link. Now, SSH has interactivity requirements that if you type on the keyboard, a packet has to be sent. Otherwise, you lose the interactivity that you are expecting from SSH. So basically, by getting timestamps on the packets on the network, you basically get the typing behavior of the user on the keyboard. And that's an old trick that has been done in embassies all over the world for many years. You listen to somebody typing, of course you know who it is typing, but you also know what they are typing. And so here you measure a inter-packet latency in the order of 100 milliseconds. Then you don't get much information, you get 0.5 bit information. But if you measure something in the order of 250 milliseconds, these are the results of Dave Wagner, then you have already 2-bit information, 2.5-bit information about what was typed. Now, the fact that this is without any a priori information. You don't even know that the person is typing English. If you have a priori information, the data rates go up dramatically. So now then it becomes completely relatively simple to break passwords, and that's of course why newer versions of SSH batch the password, and they send it out as one packet and not as individual packets. But of course that doesn't work when you tunnel, that doesn't work for the rest of your interaction. What else can you do by counting packets or getting the timestamps of packets? This one is our results of listening to a bunch of machines and look at how their timing is. If you look at power spectra of the time series of those packets that are being sent, you can distinguish the operating system. So here in this particular case, we have a bunch of Linux boxes, a bunch of Windows boxes, and it's very easy to figure out what is what, because that has to do with buffer allocation and so on. If you look at something else in the real-time community, we talk about arrival curves, and these are, if you look at mean square error in the arrival curves, then you can distinguish what the hardware configuration is. This is work done in one afternoon by a non-interested student. So you can imagine how easy it is to get additional information if you get somebody who has the right motivation. Gosh, this is a bit difficult to read. What we have been doing is we have been doing work on remote bot detection. This is in this particular case of honeynets. When you run a virtual honeynet, you need to emulate the timing behavior of the nodes on your honeynet. And the timing behavior is typically done through timers. Now, we know that the timers, and we tend to forget that timers are managed by the timing subsystem of the operating system, and that typically doesn't work that well. So just by looking at the response time distribution of a bunch of ping packets that we send, we get 100% accuracy in determining whether we are talking to a bot or to a honeypot or to a real machine. This is getting a little bit easier with, this is a little bit more difficult, this type of attack, and I apologize that it's difficult to see. For newer versions of the Linux kernel, it's still a problem if you run these things on Windows. But we still, even with newer versions of the Linux kernel with very high accuracy, we can detect just based on the timing behavior with very few packets. At the bottom we see it's 30 packets, 30 ping packets. We know already whether it's a bot or not. We play the same game with GameBots as a result of a inter-response time distribution of responses that come from a Rangarok a bot. So it's completely trivial based on the timing behavior to determine whether a particular player is a bot or not. Other people have been doing similar work, traffic analysis for bot detection in multiplayer games, as well. So what you would like to do is you would like to obfuscate the timing behavior you have, your system is displaying. And so one way to do it is through link padding. What you do is you embed your actual real traffic into a constant stream of traffic that is just on the network, right? So you have this constant stream of boxed cars that come out, and some of them contain a car and some of them don't, right? And so that's what we are playing. This is a particular system using some appliance-based implementation of it. And so the idea is, of course, you always would like to make the observer see a constant stream of packets. That's a black line. And then maybe the real traffic is the red line, and so you need to add the green traffic to it so that it becomes. And so we have done a lot of experiments in this particular area. And the bad news is that you can listen radio on that cover channel. If you look at the entropy of the fine timing distributions, you can, now in this particular case, the red line is our estimator of how much traffic is being sent. The blue dotted line is the actual traffic that is being sent. So we very accurately, with very low latency, detect whether traffic is being sent or not. Of course, you can add noise to it. Doesn't change the situation. Now, there, our estimator is barely visible, but it follows that dotted line as well. So link padding, unless you implement it extremely carefully, and that has to do with the interrupt behavior in the system. When a packet comes into your appliance, it causes a hard interrupt and hardware interrupt, and that disturbs the outgoing traffic. And so this is a system. This particular system here, we added noise to make it more difficult to detect, but it still is a problem. Another application is, so I'm now going to change mode a little bit and talk about scenarios, is you would like to build a naive implementation. Right? This is not going to be, this is a system that is not as sophisticated as Tor, for example. But you do a naive implementation of a mixed network. And what you would like to do, mixed networks, they reroute the traffic, they encrypt the traffic, and in order to prevent the timing correlation between incoming and outgoing packets to the network, what they do is they perturb the traffic in the time domain, right? Should be a good idea. You buffer the packets, you send them out after a while. So if somebody has to determine where does an incoming flow end up eventually, so this particular case, we have the incoming flow, we may know statistics about the incoming flow, and we would like to know where does it go out. That particular problem should, in theory, become more difficult if you perturb the traffic inside the network. Now, if you do a careful statistical analysis here, this is using entropy analysis. And, what we see there is a little line with little blue dots. That's the S0 line. That is just a proxy. That thing doesn't do any perturbation. And the Y line is the detection probability. What is the probability of correctly detecting where the flow is going? And what we see is if we don't do anything, we are better than most of the perturbing schemes that we could come up with. And that has to do with the fact that typically that we are not perturbing just UDP traffic. We are perturbing traffic that is controlled by TCP, which is a feedback control at the two ends of the host. So if you start perturbing the traffic and you play with the timing behavior, you have the two end hosts starting to pump. The feedback control kicks in, and your timing footprint becomes bigger. Also, you would think that if you had more nodes in your mixed network, that then the protection would be better. Actually, the more nodes you have, the more you disturb the TCP behavior, the bigger become the timing footprints, the worse is the behavior of your system. Again, this is a naive implementation. I just would like to make the point here. And they can tell you all about a more sophisticated implementation. Other question: can you hide in a crowd? So we immerse ourselves in clouds and hope that nobody sees what we're doing. Well, what we have done here is why don't they see what we are doing? Is because the observer only gets access to aggregated data, right? So example is you have a preferred customer card from a store, and what you do is you switch this card with all your friends, right? You perturb those cards so that eventually the company only gets access to aggregated data. What I'm going to show you is that that's not going to help. What we have here is measurements on aggregated data that goes into a little switch and comes out from the little switch. So we don't know, we cannot distinguish the flows because we have only access to aggregated data. We only count the packets that go into the switch and packets that go out at the individual ports. What we can do is we can reconstruct exactly what the flows were. And the way this is done using a statistical signal processing methodology called blind source separation, which I would like to illustrate here just for a second. On top we have the original signals. These are your flows. What the observer sees, and it's a little bit difficult to see maybe, the observer sees only aggregates. It sees overlaps of those figures. It never saw the original signal. And at the bottom we see what the observer can reconstruct. So it's like solving a linear equation: x is equal a y, but you need to reconstruct x, but you don't know y, but you don't know a either. Here, this is an application where you have a whole bunch of people talking to each other. All we do is we count packets. We count aggregates of packets. We don't know whom those packets belong to, and we can reconstruct the communication matrix. This gets even worse when we go into wireless network. When this is a work that we did on a completely anonymized network. It uses anonymization of MAC addresses, of IP headers. The IP headers are encrypted. It uses link padding, perfect link padding, and we can still separate the particular nodes in the system who just they all send the same traffic, but we can still separate them by putting a bunch of sensors into the network. And the sensors, what they can do is they can only count packets. That's all they do. So here we can use the separation to then do intersection and try to locate where the senders are. And in that particular case, we have very accurate estimations. The blue areas are the locations where we think the senders are. It's very accurate. We can also reconstruct the route. In this particular case, we have a sender, we have a receiver, and we know where the sender is. That's easy. But where is the receiver? And we have an area that where the receiver could be. And again, this is all done using blind source separation. The last slide, I would like just to show a little bit of some work that we just started to do, and that has to do with voice over IP. Voice over IP, and if it is end-to-end, voice over peer-to-peer, voice over IP has to be a good citizen, so they have to do silent suppression. If people don't talk, we don't send packets. The problem is the moment you do silent suppression, you pass a lot of information to an observer. Here, this is a stream of packets. On the side, we have I don't know what it is, either reel maybe or something that shows us what kind of packets are being sent. The moment silent suppression kicks in, we go from a 50 millisecond, 50 milliseconds into packet time, 60 milliseconds into packet time to 100 milliseconds into packet time. That we can